Same thing you can visualize on this PPT. This is the shear force diagram and this is the bending moment diagram. Now let us go for a next particular problem, where in this particular problem 1.2 meter length subjected to the UDL 20 and the remaining portion no load is applied over here. So now what is the variation of shear force along the length of the beam and what is the variation of bending moment? Let us visualize in this particular problem. As usual, our step number 1 is to find out the support reactions. Sigma H is equal to 0, RAH is equal to 0 as there is no force or no load is acting on this particular system. Sigma V is equal to 0, RAV assuming as it is upward, this 20 into 1.2 acting downward, so RAV minus 20 into 1.2 which is equated with 0, we achieve RAV is of 24 kilonewton. This is the reactions that we achieve over here. Taking third equilibrium condition, sigma MA is equal to 0. Summation of all the moment of the forces at A is equal to 0, assuming the moment at A, MA acting of anticlockwise sign, so minus MA plus 20 into 1.2, that is the force or load, multiply by the distance 0.8 plus 1.2 by 2 because my CG is over here. So from here to here I have to take a distance 0.8 plus 1.2 by 2 is equated with 0. By simplifying this equation we can get MA is equal to 33.6 kilonewton into meter. That is the moment acting over here. Positive sign indicated that our assumed direction of MA is of anticlockwise nature at A is right. Let us go for plotting of shear force diagram. Let us be understood over here. At over here, no load or at the tip, no force is acting, the shear force is 0. Up till the 1.2 meter UDL is acting, the variation which is given by inclined straight line, and the ordinate is of 20 into 1.2, 24 kilonewton. In this 0.8 meter region, there is no load is acting, the variation is given by horizontal straight line. So it is constant 24 up to the end of beam, that is up to the support of beam, that is the 20 kilonewton. This is the variation, or this is the shear force diagram. This diagram shows the variation of shear force along the length of the beam with the positive value as per our sign convention. Let us be understood by taking over here the same problem on the tabletop. The length of 1.2 meter subjected to UDL 1.2 meter, this is of 0.8 meter, B, A and C. Baseline. Take a section over here, (20 kilonewton per meter), length is of x. So SF at x is equal to 20 into x, section right downward treated as positive. Now if we put x is equal to 0, SF at B is equal to 0. Now this UDL is up to the 1.2 meter only. So if we take x is equal to 1.2, SF at C is equal to 20 into 1.2, that is of 24 kilonewton. So this ordinate is of 24, these ordinate is of 0, UDL is there. If you want to take more precisely, you can take the intermediate point of 0.6 meter, x is equal to 0.6, SF is equal to 20 into 0.6 is equal to 12 kilonewton, and join these 3 points, we can achieve inclined straight line, plus sign. Now let us take a section over here. Then my beam is of like this. X, shear force at x is equal to 20 into 1.2, that is equal to 24, because there is no load is acting over here, and my full UDL is coming into the region of section X. So this ordinate at section X is 24. So at all these points the variation of shear force is of 24 throughout. Joining all these points, we can achieve horizontal straight line. This is my shear force diagram. Now let us go for plotting of bending moment diagram. The given beam is of cantilever beam, (20 kilonewton per meter), length is of 1.2 meter, and up to 0.8 meter there is no load is acting. A, B, C. So I am plotting these lines at various important points. Baseline. Now let us take a section over here in the region of CB, section XX. B, this is section XX at distance X. This load is of 20 kilonewton per meter. So shear force at XX, as we know, it is 20 into X, but bending moment at XX is equal to 20 into X by 2. Sign convention, section right clockwise creates the hogging moment, which is of negative sign, is equal to minus 10 x square. So if we will put in this equation x is equal to 0, bending moment at B comes to be 0. Now let us find out at 0.6 meter, then find out at 1.2 meter. Let's find out bending moment at 1.2 meter is equal to minus 10 into 1.2 square, and this we achieve as 14.4 kilonewton into meter with the negative sign. So this ordinate is of 14.4. As we know, the UDL is there. Also, it will be verified from this equation. It is parabolic nature, and from the previous problem we found out this parabola which is of this nature. with negative sign. Now let us find out the bending moment at A. That is, if we take a section over here at XX. Let us draw the free body diagram. (20 kilonewton per meter). This available length is of 1.2 meter. This total length at section XX from B is of X. Then bending moment at XX is equal to minus sign 20 into 1.2 is the total load which is acting, into the CG distance is of here, so 1.2 by 2 plus I am interested with this distance, that is nothing but X minus 1.2. So we will achieve minus 24 bracket X minus 0.6. Now we will put the value of X as we know the values up to 1.2. So we have to go ahead, X is equal to, put the value 2 meter. Then in that case bending moment at A is equal to minus 24 bracket 2 minus 0.6, which is equal to 33.6 kilonewton into meter. So here we achieve as it is 33.6. And just see this equation, it's a linear equation. We can join this by horizontal straight line. So this diagram you can visualize, this is of parabola, this is the inclined straight line. So now we can easily plot the bending moment diagram by using our basic concept also. The same thing we can visualize over here. For this UDL, this variation is given by parabolic nature, and for this up to 0.8 meter there is no load is acting, hence the variation is of inclined straight line. Let us go with the next problem. Here in this particular problem, the combination of two different load which has been given to us, UDL as well as this point load. Now recall our basic fundamentals. Then as we know, the first step is to find out the support reactions, but even though we can plot the shear force variation diagram and the bending moment variation diagram without the finding out the support reaction also. So visualize over here support reactions. As we know, bending moment diagram, 0 over here, no load is acting. Up to 1 meter UDL is Z, so 30 into 1, 30, variation is given by inclined straight line. Then there is no load between these 2 points, so 30 is remaining constant, so horizontal straight line. This 20, now you just see the case 20. If we take a section over here, these both the loads are acting downward. So if we take a section over here, both the loads are acting section right downwards, which is treated as positive. So 30 into 1, 30 plus 20, 50. This 50 kilonewton is achieved over here. And there is no load is acting over here. Horizontal straight line 50, and we achieve the RAV as 50 over here. So we can achieve the shear force diagram you can plot by taking a section over here at your home also, at your room also. Next, bending moment diagram. 0 over here because force or load is 0. At 1 meter, 30 into 1 into 1 by 2, that is 30 by 2, that is 15 variation which is of parabolic nature. Here between these two there is no load, variation which is of inclined straight line, but the value is of 30 into 1 into bracket 0.5 plus 1 by 2. 0.5 plus 1 by 2 is 1. So 30 into 1, that is of 30, and this is inclined straight line variation. Now at this junction, the bending moment value is of 30 into 1 into bracket 0.5 plus 0.5 plus 1 by 2, that is 0.5 plus 0.5 is 1, 1 plus 1 by 2, that is 1.5. So 30 into 1.5 plus 20 into 0.5, answers comes to be 55, and there is no load between these 2 points. It is of variation of inclined straight line, and nature is of minus sign as the hogging moment generated in this cantilever beam. So likewise we can plot the shear force and bending moment diagram using the concept as well as by taking the sections also. Remaining problems like beam with UVL as well as beam with the concentrated moment we will discuss more about into the next section. Thank you.